وصحبه أجمعين. This is the last section in chapter 3, which is about using the mean and standard deviation together. So we will mention here some points in which we use the mean and the standard deviation together, some concepts. So the first concept is the coefficient of variation. The standard deviation measures the variation in the data. We studied this in 3.2. For decision makers, the standard deviation indicates how spread out a distribution is. So it measures the variation or the spread. For distributions that have the same mean, the distribution with the largest standard deviation has the greatest relative spread. So if the two distributions have the same mean, for example, quiz 1 and quiz 2, they have the same mean, then the largest standard deviation would mean the greatest relative spread. But if the two distributions have different means, okay, especially like a quiz and a final, this is out of 40, this is out of 10. So the means would be different, much different. So in that case, we cannot use the standard deviation to measure the spread or to compare the spread of the two distributions. To compare the spread of the distributions, if the means are different, we use the coefficient of variation. So the relative spread cannot be determined by just comparing standard deviations if the means are different. You have to use coefficient of variation. So when or why do we use coefficient of variation? We use it to measure the relative variation for distributions with different means. The definition of the coefficient of variation, it is a ratio, okay? So it is the ratio of the standard deviation to the mean expressed as a percentage. So it is the ratio of the standard deviation. In case of population, it is called sigma. The standard deviation of the population is sigma over the mean of the population, which is mu, as a percentage. So we multiply by 100%. In case of sample, standard deviation of the sample is S. The mean of the sample is X bar. So we divide S by X bar times 100%. So it's always the ratio of the standard deviation to the mean. It measures, coefficient of variation is used to measure, it measures variation relative to the mean. This is very important. So coefficient of variation measures variation relative to the mean. So it measures variation. It's a measure of variation. If you remember in section 3.2, we said we have 4 measures of variation: range, variance, standard deviation, and coefficient of variation. But we did not study coefficient of variation in 3.2. We studied it here because it uses the mean and the standard deviation together. So it's a measure of variation, but relative to the mean. So the mean should be down below, and the variation should be in the numerator because it's a measure of variation. So remember, coefficient of variation, the measure of variation would be up in the numerator. Okay? Not to forget that the standard deviation is always up when we evaluate the coefficient of variation. When the coefficient of variation for 2 or more distributions are compared, the distribution with the largest coefficient of variation is said to have the greatest relative spread. So we can compare the spread of the two distributions when they have different means by computing the coefficient of variation, and the one with larger coefficient of variation would have larger relative spread. In finance, it has a very nice application, the coefficient of variation. It is one of the measures of the relative risk of a stock portfolio. So it's it's a measure of the relative risk of a portfolio. Assume here, this is an example. Assume we have two portfolios. Portfolio A, collection of stocks with average 12% return and standard deviation 3%. And another portfolio B of stocks with average return 6% and standard deviation 2%. Now, since the means are different, this is 12%, this is 6%, you cannot just say that portfolio B has 2% standard deviation, less than 3%, so it has less spread. It's less spread than portfolio A. No, this is not correct. You cannot compare using the standard deviation because the averages are different. So how to compare the spread, the relative spread here? You use the coefficient of variation. So you find the coefficient of variation of portfolio A by dividing the standard deviation, which is 3% over 12%, 3 over 12, times 100%. Don't forget to multiply by 100%. You get 25%. So the coefficient of variation of portfolio A is 25%. The coefficient of variation of portfolio B, 2 over 6 times 100%, would be 33%. So now you can compare and find that the coefficient of variation of portfolio B is greater than the coefficient of variation of portfolio A. So portfolio B is more risky than portfolio A. Okay, although portfolio B has a lower standard deviation, but it has a higher coefficient of variation. So it's more risky because the coefficient of variation is higher. The spread is more. The spread is more, so it would be more risky. I mentioned here 3 questions about the coefficient of variation. This is an easy one, a straightforward. You just compute the coefficient of variation for population 1 and population 2. So coefficient of variation of population 1, for example, would be sigma over mu times 100%. You find the answer, and you find also the coefficient of variation of population 2. And based on your answers in part A, which population has data values that are more variable relative to the size of the population mean? So the one with the larger coefficient of variation would have more variable. Okay, would be more variable data values. Okay, 351. Let us answer this one. 2 distributions of data are being analyzed. Distribution A has the mean of 500, standard deviation 100. Distribution B has a mean of 10, standard deviation 4. Based on this information, use the coefficient of variation to determine which distribution has greater relative variation. He could ask you also without saying use the coefficient of variation. He can say immediately, based on this information, determine which distribution has greater relative variation. So to measure or to compare the relative variation, if the means are different, you need to find the coefficient of variation. If we find the coefficient of variation of distribution A, we divide the standard deviation by the mean times 100%, and the result would be 20%. If we find the coefficient of variation of distribution B, the standard deviation in this case is 4, the mean is 10, times 100%, so it is 40%. So you can say that the coefficient of variation of B is greater than A, so distribution B has greater relative variation. That's the answer. Also, this one, 3.54, you can use the calculator to compute the mean and the standard deviation of for the sample selected from population A. So please use your calculator to find the mean and the standard deviation for the sample A. Also, here find the mean and the standard deviation of sample B. And then to answer this question, which sample has the greater spread, you find the coefficient of variation of sample taken from population A and the coefficient of variation of sample taken from population B. And sorry, you do this here. You do this here. But here, he doesn't want the coefficient of variation. If we read the question carefully, he says, which sample has the greater spread when measured by the standard deviation? So if you just use the standard deviation as a measure, the sample with higher standard deviation would have greater spread here. Of course, we cannot do that because the means would be different, but he wants to compare, he wants you to compare here between using the standard deviation as a measure of spread in this case and using the coefficient of variation here, which will give you the correct measure in this case to compare the spread. Okay. The second point in this section is about the empirical rule. And the empirical rule is a rule used for bell-shaped distributions. So we use this rule only with bell-shaped distributions. We will study in details bell-shaped distributions in chapter 6, and we will see exactly why these percentages are true, are correct. The rule says that now we need also to use, remember section 3.3 is about using the mean and the standard deviation together. So the mean is here in the middle, in the center, and the standard deviation measures the distance from the mean. So we go to the right of the mean by units of standard deviation. Here, this point would be mu plus sigma. So we went sigma units to the right of mu. And if you go sigma units to the left of mu, you will reach the point mu minus sigma. So this point is the point mu minus sigma, and this point is the point mu plus sigma. So for example, if mu is 10 and sigma is 2, so this would be 10 and this would be 12 and this would be 8. Okay. Now if you go another standard deviation to the right of the mean, so you will reach the point mu plus 2 sigma, which is 10 plus 2 times 2, that's 14. So this would be 14, this would be 2, and this is 10, and this is 8. If you go 2 standard deviations to the left of the mean, then you have 10 minus 2 times 2, and 10 minus 4, which is 6. Okay, so this is an example how we use the standard deviation as a measure of the distance from the mean. Now, this interval from 8 to 12 is called the first interval, mu plus or minus sigma. It's the first interval. And the first here from, because 1 sigma. This one is the second interval because we go 2 standard deviations. So we call it the second interval. If we go 3 standard deviations, we call it the third interval. Okay? The rule says that in the first interval, you have approximately 68% of the values. So if you have a data with mean 10, for example, and standard deviation 2, I don't know the data, I don't have the data, but if I know that the data has bell-shaped, then I am sure that 68% of the data are between 8 and 12. So 68% would be in the first interval. Since it is a mound-shaped, it is symmetric, so if you divide 68 by 2, we have 34. So 34% of the data would be between mu and mu plus sigma, and 34% of the data would be between 8 and 10, or mu minus sigma and mu plus sigma. So this is what we get from the first information here. The second information, that if we go to the second interval, then 95% of the values are in the second interval. Again, 95% between mu minus 2 sigma and mu plus 2 sigma. So between 6 and 14. So 95% of the data are between 6 and 14. But we know that 68% of them are between 8 and 12. So between 6 and 8 and 12 and 14, we have 95 minus 68%. So if you subtract 95% minus 68%, you get 27%. And if you divide by 2, you get 13.5% of the data are here between mu plus sigma and mu plus 2 sigma, and also 13.5% of the data between 6 and 8, or between mu minus 2 sigma and mu minus sigma, because the distribution is symmetric. It's bell-shaped, and any bell-shaped distribution is symmetric. Now, what about after mu plus 2 sigma and after mu minus 2 sigma? We have 95% here, so what is left is 5%. The distribution is symmetric, so 2.5% are to the left of mu plus 2 sigma, and 2.5% are to the right of mu minus 2 sigma. If you go 3 sigmas from the mean, then this interval, which is 3 standard deviations to the right and 3 standard deviations to the left of the mean, will contain virtually all of the data, almost all of the data, or approximately, you can say approximately 99.7% of the data, if the distribution is bell-shaped. So you have all of this information about any bell-shaped distribution. Let us answer this question. Question 355. Consider the following sample. Calculate the mean and standard deviation for this data. To calculate the mean, I will use the calculator and the standard deviation. So I will go to the mode stat, 1 variance, and I'll enter the data. So 22, and then I write equal, and then 46 and 25, and so on. If you have a calculator, please try to calculate and get used to evaluate the standard deviation and the mean using the calculator. So 48 plus 86 plus 41 plus 13 equal, sorry, not plus, and 49 equal, you always put equal, it's like enter in the computer, and the last row 72, 70, 91, 51. Imagine that this question comes in the exam and you don't have a calculator, or you don't know how to compute the standard deviation using the calculator. You will not be able to solve this question on time. So I put the numbers, and he said 30. The last one is 30, so you can count that you have 3 columns and 3 rows and 10 columns. So in fact, you have 30 numbers. After that, you put in, you press on, and shift 1, shift stat, and you press 4, which is variance, and 2 will give you the mean. He said that this is a sample, so we will use the sample notation. So X bar is 51, and S is the standard deviation. You go to shift 1, then variance, then number 4, SX, it would be 22.6. So 22.6 is the standard deviation of this sample, and 51 is the mean. Okay, part B, determine the percentage of data values that fall in each of the following intervals. This is the first interval, this is the second interval, this is the third interval. Let us first determine the first interval. The first interval, okay, is from X bar minus S to X bar plus S. That's the first interval. So we have X bar and S here. So we find 51 minus 22.6 and write it here. So it's 28.4. And we add X bar plus S and write the result here. So the first interval contains all the numbers between 28.4 and 73.4. What is the question? Determine the percentage of data values that fall in this interval. Yani what is the percentage of values that fall in this interval? How to find the percentage? I need to know how many of these numbers, the 30 numbers, how many of them are here between 28 and 73. So let us find all numbers between 28 and 73. These two are not. 72 is okay. 46 is okay. Okay. Between 28 and 73, this is not. This is not. Between 28 and 73, this is not. 86 is greater than 73. Between 28 and 73, this is okay. This is okay. This is not. This is not. This is not. 28 and 73. This is okay. 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 This is not. This is not. This is okay. This is not. 28. This is greater. This is greater. This is less than 73. So all of these numbers fall in the first interval between 28 and 73. How many are they? Let us count them. 3, 6, 9, 10, 14, 15, 19. There are 19 numbers. 19 numbers. How to find the percentage of these 19 numbers? I divide by 30, multiply by 100. This will give me the percentage of these 19's numbers. So I will get 63.3. So this is the percentage of the data values that lie in the first interval. Does this agree? Is this okay with the empirical rule? Empirical rule says if the data is bell-shaped, you will have approximately 68%. Approximately 68%, by the way, means 68 point something, 0.3, 0.4, 0.5, like this. But 63 is somehow away from 68. So this data might not be mound-shaped because we have 63.3, not 68. We can do the same for X bar plus or minus 2S. Find the interval. So 20, you start by 51 if you like, and subtract 2 times 22.6, you get 5.8. and this is the left end. And if you add 51 plus 2 times 22.6, you will get 96.2. Now, I need to find how many numbers between 5.8 and 96.2 in these numbers. Well, the smallest is 12. It's already greater than 5. And the largest is 91, which is already less than 96. So it seems that all of these numbers are between 5 and 96, which is the case. So I have 30 numbers, and 30 over 30, if you multiply by 100, you get 100%. So 100% of the data lies in the second interval. Here he said in the mound-shaped 95%. We have more than that, so this is not really a mound-shaped sample. You can also find x bar plus or minus 3s because he asked for it. Please find it's from where to where, but the answer would be for sure 100% because this interval is larger than this interval. Now compare these with percentages that should be expected from a bell-shaped. So in x bar plus or minus s, the data, we can say that this is the data, and this is empirical rule. The data has 63.3%. Here he says approximately 68%. In the second interval, here we have 100%. Here he said, the empirical rule said 95%. And the third interval, we have 100% actual. The actual data has 100%. Here we have 99.7%. These are the differences. Does it seem plausible, possible that this data came from a bell-shaped population? Well, it's okay. You can say, yeah, it could be. Okay, it could. Because this is a sample, you know. This is a sample, not the population. He says from the population. It could be taken from, it's possible, and it's not possible also because the numbers are different. So we can say it's okay. It could be taken from the population, which is bell-shaped. If he asks you a question like this, use the empirical rule to describe the distribution. Describing the distribution, you mention all the 3 points. You say approximately 68% of the data values are between, and you put the intervals x bar minus s and x bar plus s. So here x bar, the mean is 15.1, so 15.1 minus 3.1, which is the standard deviation. Okay, so the answer is 12. So 68% of the data are between 12, and now you add 15 plus 1 standard deviation, you get 18.2. So this is how we describe the data. We tell him that we don't have the data, but we know that approximately 68% of the data are between 12 and 18.2 because he said bell-shaped and he said use empirical rule. Also, you can continue 95% are between and 99.7% are between. You can continue the question. Let me end by this exercise. Let me finish by this one. The results of a national survey showed that on average, this is the average, 6.9 hours per night, average of sleep, standard deviation 1.2 hours. Assume that the number of hours follows a bell-shaped, good, so we can use the empirical rule. Use the empirical rule to calculate the percentage of individuals who sleep between 5.7 and 9.3. So I know that 6.9 is the mean, and I'd like to know what percentage of individuals will sleep between 5.7 and 9.3. Well, I will be able to answer this question if I can find out 9.3 is where? What is the distance of 9.3 from the mean. How many standard deviations did we go to the right from the mean? Okay, to find how many standard deviations we moved from 6.9, you simply find the distance between 9.3 and 6.9. This is the distance between these two, and you divide by the standard deviation. So by this, you will know that how many standard deviations. You will find that the answer is 2. Actually, this is a mu plus sigma, and this is a mu plus 2 sigma. Now 5.7, you do the same. You subtract 5.7 from 6.9. You divide by 1.2. You will find that the answer is -1. So 5.7 is actually mu minus sigma. Mu minus sigma. So we went 1 standard deviation here, but here we went 2 standard deviations. So now the question is clear. What percentage of data lies between mu minus sigma and mu plus 2 sigma? I go to this shape. Where is mu minus sigma? This is mu minus sigma. And this is mu plus 2 sigma. So how many? What is the percentage between these two from here to here? I can add 34% plus 34% plus 13.5%, and that would be the answer. So the answer is 34% plus 34%, it would be 68%, plus I add 13.5%, and this would give me the answer, which is 81.5%. I stop here and I open the floor for the questions. Please, if you have any question, feel free to